Tangent planes and linear approximations. So this topic is probably going to be rather short. I think there's not too much to say about it. The first thing is that, is to kind of recall the analogous version of this from Calc 1. So in Calc 1, you learned about the notion of the tangent line to a curve at a point and how the derivative helps you to create such a tangent line. And you also learned the idea of linear approximation, or uh, creating a linear approximation to a function at a given point. And you learned that these two notions are the same. The equation that describes both of these things is this one. I've written it in the linear approximation version. If you want it in the tangent line version, this would be a y. And I mean the intuition, if you don't remember, this is to get the height correct, to make it so that you end up passing through the point. I guess you pass through the point x comma f of, or not, maybe not x, a comma f of a is the point that you are basing your linear approximation at, or that you're making your tangent line tangent to the curve at this particular point. So this is to get the height of your tangent line correct, and then the slope of the tangent line is calculated by using the derivative of the function and plugging in at a. This is to match up the slopes of the curve, match up the slope of the tangent line with the slope of the curve at that point, so that you end up getting a tangent line. Okay, right, and this can be viewed in like the point slope form. If you move the f of a to the other side, then you end up with y minus y naught equals mx minus x naught. So that's a way to view this in point slope form. Okay, so that was linear approximation. That was Calc 1. And the idea is that this generalizes to higher dimension. We're only going to be dealing with one more dimension. So if you instead have a function of two variables, f of x and y, equals to z, let that be the, instead of curve, we now have a surface, and we want to talk about the tangent plane instead of the tangent line. We want this tangent plane to be parallel to, not parallel, but we want to be tangent. We want it to just touch the surface at a given point, which I'm denoting by p naught, which is x naught comma y naught. Well, then you have this formula. So z is equal to, you can treat this as z naught, right? This is the height that you want to place your tangent plane at, and then you want to match up the derivatives. You want to match up the slopes in the x and y directions. That's why we have these derivatives now. Recall that this is the notation for a partial derivative. So the slope, if you move in the x direction, and the slope that you move in the y direction. That's what these two quantities represent. And the x minus x naught and y minus y naught are just to center your plane so that you end up capturing the point x naught comma y naught. Right. So hopefully you can see the analogy between the one-dimensional case in Calc 1 and the two-dimensional case that we have now in Calc 3. And just like how tangent line and linear approximation were equivalent notions, tangent plane and linear approximation are equivalent notions, as you can see. This is the formula that you would have for the linear approximation, and the only difference is that instead of z, we have this L of x and y. As we end up thinking of this whole thing, instead of geometrically, we think of it as a function whose inputs we could when we plug in values x and y, they're really close to convenient values x naught and y naught. Then this can be used to approximate the function f, as long as you're close to x naught comma y naught. It's the idea of linear approximation. Okay. Let's see some examples. So I just grabbed two examples that are creating equations of tangent planes, similar to your homework. So Suppose you want to create the equation of a tangent plane to this given surface at a given point here. So the process is you're going to want to compute, well, these three quantities, the f of x naught y naught, f prime of x naught y naught, or not f prime, I should say f sub x of x naught y naught, and f sub y of x naught y naught. So you want to compute the x derivative and the y derivative, and then you want to plug in the point that you're trying to construct your tangent plane at. So I'm splitting it up into, I organize my work into columns. So here we take the x derivative and the y derivative. So let's just talk through that, just in case you're still getting used to this. So the partial derivative of this function. All right, so both x and y treat this, well, there are x and y in the inner function. So ln is a function of x and y. So when you take the partial derivative, you will have to take the derivative of the logarithm. And then with the x derivative, the y is treated as a constant, and you end up having this 2x. So the constant disappears when you take the derivative, right? So this y disappears with the x derivative, and then this 2x becomes a 2, but you're just doing the chain rule at that stage. The y derivative, so you have the derivative of the ln function, and then when you do chain rule, well, 2x is a constant with respect to y, so when taking the y derivative, this term goes to 0. Take the y derivative, this term goes to 1. So you end up with a 1, or well, time is 1, which automatically you can not write that. So those are the x and y derivatives. Then you plug in. So you plug in f sub x and f sub y at the point that you're trying to base your tangent plane at. So that should be straightforward. You get certain values, and then you write your equation of the plane in the form, right? So you have your constant, which is f at the point. Then you have the x derivative times x minus x naught. Well, x naught in this case is minus 1, so you get a plus 1 here. And then the f sub y is, you get 1, so 1 is there. And then y minus y naught, so y minus 3, as you can see. Okay. Next, so very similar type of problem. I could have made it more complicated, but I didn't feel like making something completely crazy. So again, you have a function, a surface, and you want to make a tangent plane at this point. So you take your function, you take the x derivative, take the y derivative. So let's just slowly think through that. So with the x derivative, the other terms go to 0 because they're constant with respect to x, and you just have a 2x over 16. So I think that's pretty clear. And then with the y derivative, well, these two terms go to 0, so you just have this as being non-zero when you take the y derivative, so you get 2y over 9. Okay, then you plug in at the point, and then you collect things together into the formula for the tangent plane. Right, so z is equal to f at the point, f sub x at the point times x minus x naught, f sub y times y minus y naught. So that's that should be clear. And then the other concept that's part of this section is this notion of a differential, and in particular the total differential. So I try to write about it here, but I think the easiest way to see it is just through an example. But the idea is pretty similar. So with the how do I want to say it? So so these were like the slopes at the points that we just did with the tangent planes. Dx is like the x minus a and y minus b, or x minus x naught, y minus y naught. These are like the small changes in the x and y, whereas these are just matching up the slopes. and dz is like the change in the variable z. If you were to make those like small increments in x and y, the total differential has to do with just summing up all of the changes that you could make with all of the variables. So the OpenStax text only gives you like this expression, and you're supposed to generalize this to your problem, which has three variables. So I created one that has three variables as well. And the problem actually doesn't give you a particular point. So I did the same thing. So notice that in this definition, it says like, okay, if you were basing it at the point x naught, y naught, then you'd be evaluating the derivatives at the point. But here, because we're not given a point, we just have the variables without any subscripts. So let's see. Taking the t derivative gives you this term, and then you have dt for like small change in t if you had that um, in the practical version of the problem. And then dr also, you take the r derivative, and then you also have to take the s derivative because there were three different variables. You could view the function u as a function of t, r, and s. Okay, and so that's how you know that you would have three terms in your total differential. It's going to be the summing up all of the partial derivatives, basically. Summing up all of the individual partial derivatives that you could create. Order 1, I guess. And that's all I have for this. So should be good.